Okay, now what were we talking about? We were talking about the number of carbon atoms, right? So I told you
Yeah.
that in this question, you've got a saturated alcohol, the MM plus 1 peaks are given. So you can find the number of carbon atom using the formula, which is 100 over 1.1 into M plus 1 divided by M. What do you get? What's the number of carbon atoms?
Oh, okay.
Nikya, what's the number of carbon atoms?
Four.
Okay, so it's coming out to be 4, right? So you've got 4 carbon atoms. Now remember, don't try to figure out the structure of a molecule by looking at the NMR spectrum, because you can get a lot of information about the molecule by just remember it's a saturated alcohol, right? So it's a 4 carbon atom alcohol, and he's also given us the M peak value, which is 74. So that means the MR of this molecule is 74. Right, so they've given us the molecular ion peak as well. That's at 74. So I'm going to make a 4 carbon atom saturated alcohol. So isomers are really helpful. So 4 carbon atom saturated alcohol. So that's OH. Is this, and all of the others are hydrogen atoms. So that's 10 hydrogen atoms. 3 plus 2, that's 6. That's 10 hydrogen atoms. So this comes out to be 74. 4 carbons, that's 48. 48 plus 16 is 64. And then you have 10 hydrogens. So this would be 74, right? So that is one possible arrangement. But knowledge of isomers is going to be really helpful, because the alcohol could have, the same alcohol, saturated alcohol, could have many different shapes. The OH could be on the second carbon atom. So you could have a molecule where the OH is on the second carbon atom, and that's still 74. But is this point clear?
Yes, sir.
Okay, so I know a lot of information about this molecule, but I don't know which exact molecule are we talking about. There could be another one that the carbon atoms could be in a branched. They could be a branched version of this. So this could be OH, and this one would have H and H, and there's going to be another carbon with 3 H's, and this one would be, and this one will have, so all of them are 74. They're all isomers of each other. Or I could have a 4 carbon atom saturated alcohol with the MR74. There could be another one, which is going to be this one. So 3 H's with this, and you have 3 H's with, now those are the only 4 possible candidates. So based on this information that's given over here, you've got 4 possible. So it was due to the fact that H is less shielded and is difficult. H is more shielded. That point is this point. Ek second. Let me just discuss this for a second. Bhaskar, is that question, did you send this question right now?
Yes, sir.
See, uska tha ke, I was saying ke splitting pattern, right? Last time we discussed that the splitting pattern happened because if this hydrogen proton is resonating, these hydrogen protons in the magnetic field neighborhood would be interfering with the external magnetic field, right? So the hydrogen proton over here will experience sometimes a slightly greater or slightly lesser magnetic field. Is that clear?
Yes.
So the point is, these hydrogen protons, when it's an OH hydrogen, they will not be able to interfere with this hydrogen proton or its magnetic field, because the electrons over here will be creating a shielding effect.
Okay. Yes.
So the magnetic field of these two things will not interfere, which is why this would always be a singlet peak. As anyways, coming back to the question. So coming back to the question, you've got, where's the question? This one. So I figured out that it's one of these isomers, right? 4 carbon atom saturated alcohol. Now I've been given an NMR spectrum. How many different chemical environments are there? There are 4 environments, right? So the graph shows that the hydrogen protons exist in 4 different environments. So I'll just give you a quick recap of that. I told you that if the bonding around the hydrogen atom changes even slightly, the hydrogens would resonate at a different frequency. So these three hydrogens are exactly, or they're chemically bonded in exactly the same way. These two hydrogens are slightly different, or the groups that are attached to it, they're slightly different. This hydrogen is very different from the other two. So there would be three different resonant frequencies, three different environments. This one had how many? That these two CH3s resonated at the same frequency. This one resonated at a different frequency. These two hydrogens resonated at the same frequency, and this one. So there were five or four in this case. These two are exactly the same. This would resonate at F2, this would resonate at F3, and this would resonate at F4. So even without analyzing the spectrum, the hydrogen protons have 4 environments. So I'll just go above and I'll see which one has 4 environments. How many environments do you think this one has? The first one. Like how many environments does this first isomer have?
5.
Okay, so that's 5 because you've got these CH3s, I mean the hydrogen protons over here, they're bonded differently compared to the other ones. This OH hydrogen proton is different. This CH2 hydrogen protons are different compared to the other ones. So all of them are kind of bonded slightly differently. Like this CH2 is different compared to this CH2 because this CH2 is bonded to a CH2OH on one side and it's bonded to a CH2CH3 on one side. This one, its groups are slightly different. It's bonded to a CH3 on one side. So there's a very slight difference. So there'll be 5 different. That's 5, right? 5 different environments. Is that clear? That you'll have 5 different absorptions. Is that clear?
Yes, sir.
So then you have, so that's one thing. Now, the other thing is, so that's clearly not the answer. This one does not belong to that one, right? So that is wrong. So what about this one? How many different environments do you think this one has? This CH3 is different from the others. Once again. So then you have this CH2 is different, right? This CH3 is, the hydrogen protons are different. This H is different. This OH is different, right? So again, how many different environments?
5.
That's 5, not 4, right? So then what about this one? How many different environments does this have?
4.
This one. Aren't all the CH3s exactly the same?
2, 3, 4. Yeah. Now this one looks like 2.
I mean, 2, right? I mean, all of these are exactly bonded in exactly the same way. I mean, all of them, this CH3 is bonded to COH. This one is also bonded to the same COH. This one is also bonded to the same COH. So they're all exactly bonded the same way. And this H is different. Is that clear?
Yes, sir.
Yes.
So there would be just 2 environments. So that is also wrong. So the correct answer would be this last one. This one will have 4 environments. Why 4? Because these 2 CH3s are exactly the same environment. Because this is bonded to the same CH, this is also bonded to the same CH. So they're kind of exactly the same. Then this H is different, this CH2 is different, and then this OH is different. So you've got 4 chemical environments, and that will give you this peak. Is that clear?
Yes, sir.
Yes, sir.
So the point is, okay, without even actually going through the NMR spectrum, we've been able to figure out what the structure is, and we're going to go into a lot more detail as well, because remember, he's asking for the answer, but then he's asking for the explanation as well. It's a big question. It's a 9-mark question. So basically, we figured out which one is the correct one, but we got to explain this as well. So they're going to ask us, what is this peak? What is this peak? So I'm going to open the data booklet now, and I'm going to match these peaks now. So how do I match this? the first one is the OH peak. If you look at the data booklet and look at the NMR spectrum, this is definitely not the NMR spectrum. 1 second. Where's the NMR spectrum? This is the carbon 13 spectrum. This is the NMR spectrum. Just 1 second. Just hold on 1 second. Okay, so the OH, the hydrogen proton belonging to OH, belonging to a simple alcohol, that's 0.526, right? And it's going to be a singlet peak, right? I just told you that. So this one, I'm going to do all the working on it. So this one is 0.526, right?
Mm.
And it's going to be a singlet peak because remember we told that this will not, the n+1 rule. It's going to be a singlet peak. So it's probably going to be this one, right? Like if I go and match this, it's probably going to be this one. Is that clear?
Yes, sir.
You can let me rub all of these.
Oh, yeah.
There's only one singlet, right? The n+1 rule. What was the n+1 rule that we studied yesterday? It was that if the neighborhood has n hydrogen protons, it splits into n+1 peaks, right? I mean, this is what we studied last time. That if this resonant frequency F0, if the neighborhood has 2 hydrogens, this peak would be a triplet peak. This one has too many hydrogens, 1 on this side, 3 on this side. So this one would be a multiplet peak. There would be a lot of interference because of the resonating hydrogens around it. This one would be a doublet peak. Why? Because there's only 1 hydrogen over here next to it. So this one, so that was the n+1 rule. And this one over here is going to be a singlet peak. Anyway, so let's go back. What about this CH2? This CH2 is right next. First thing, is this going to be a doublet or a triplet or a singlet? This one. How many hydrogens in its neighborhood right next door? That's
1.
one. This one is not going to be counted because the OH does not interfere with anyone. So this one is going to be a doublet, right?
Yes, sir.
सिर्फ 2 हाइड्रोजन
इसके neighborhood में I think there's only one. साथ वाले पे there's only one.
हाँ
ठीक है. अच्छा, remember I'm going to point this again. Okay, when we talked about splitting, I told you specifically okay, the OH1 and the NH2, they're always singlets. Plus, I'm going to add this as well. They don't cause any splitting as well because of the shielding effect of the lone pairs on oxygen. So this hydrogen proton would be completely separate and it will not interfere with the other hydrogen protons and the other way around as well. These hydrogen protons are not going to interfere with. So they don't cause any sort of splitting as well. So going back to this, so that's a doublet. So you've got 2 doublets. Which one is this one? So CH2 right next to oxygen. So you'll open the data booklet. So CH2, this one, CH2 right next to oxygen, that's 3.224. So that is 3.224. So I think it's this one, 3.224, this one. Right? Is that clear?
Yes, sir.
It's a doublet.
Yes, sir.
So which one is this? How many splitting would this have? This one?
multiples
Multiplet. It's because it's got 3 hydrogens here, 3 hydrogens this side, 2 hydrogens on that side. So this one will have a lot of interference and its frequency would change a lot. It's going to be a multiplet, right? So that one is a multiplet and there is a multiplet and it's a single hydrogen. So it's a very small peak because there's going to be very less absorption. So you got a multiplet peak over here. So there's this multiplet peak. And the last thing is these 2 CH3s. There's going to be a huge absorption. And that's the alkane type because right next door there's a carbon chain. So when you have an alkane type CH3 right next door, if you have a CH and right next door there's again CH3 or CH2, that would resonate at 0.9 to 1.7. And this one, what is it going to be? It's going to be a doublet. Why? Because the neighboring carbon has one hydrogen. So that's going to be a
Doublet.
doublet, right? So this one is this one, right? Is that clear?
Yes, sir.
Okay, so remember, don't directly try to solve this. Okay, it's very hard to actually figure out the structure of the molecule without writing down the isomers first. Okay, I mean that's why you study isomers a lot, because how did you figure out the structure of all the molecules that you see in organic chemistry or anywhere? The first thing is you make a lot of isomers, you make a lot of guesses. Like maybe the structure is like this, maybe it's like this, maybe it's like this. And then the NMR and your analytical techniques, they come in. And then they help us eliminate which structures are not possible. Okay, is that clear?
Yes, sir.
Okay, Baki Saim, is this clear, Bhaskar? Everyone else are clear? So the other part is that so he's saying describe and explain which type of proton is possible for each of the absorptions. You can just look at the market scheme. Basically, he's asking for what is this? The absorption at 0.9, I think. So that is this one, the CH3 hydrogen protons. Then he's going to ask you, what is this one? That's again CH, this one. Or you can just make you can draw a diagram like this and you can say that this is this one, this is this one. So you can just quote the chemical shift values. And he's talking about the splitting pattern. We just discussed the splitting pattern, so you can just quote that. And we talked about D2O last time. What did we talk about D2O? I told you that in NMR spectrum, D2O is heavy water. And heavy water has the type of proton that does not resonate. Okay, here's your D2O molecule. And it's got even numbered nucleons. So all of them are paired. So they don't have a magnetic field, which is why they're not going to resonate. So the OH and the NH2 peaks would disappear. Patani, if I had mentioned. Because of D2O, this one. The OH and NH2 peaks, they're going to disappear. So in the same question is also asking what will happen if T is dissolved in D2O. So the OH peak would disappear, this one. The peak at 2.5, that's going to disappear. That belongs to alcohol. Is that clear? Is that
Yes,
part?
sir.
So let's move to the X-rays are not in your course. Just make sure you don't attempt any questions. Maybe you might get a question on whether NMR is safe or not. I mean, your MRI scans, etc. So just remember that NMR techniques are really safe. Why are they safe? Because it operates. Or what do you need? You need a magnet. So magnets are kind of safe. I mean, we've been not harmed by magnets, right? And the other thing is you need a powerful magnet and you need radio waves. So we already deal with a lot of radio waves around us. So both of them are kind of safe. So just a small point on that. X-rays used to be in your course. X-rays are really harmful because they're very high energy. Nibaza, can you state what's your question? I'll just sum this up briefly. Okay, what does NMR spectrum tell you? It will tell you a lot of things. It will tell you, number one, the number of chemical environments. So that is one very useful information about identifying the structure. Although we wrote this in several places, but I'm just writing a short summary. Second one, it tells you the number of protons in those chemical environments. So then it will tell you about, it's going to tell you about the neighborhood. It will tell you the number of protons on the neighboring carbon. That's another very vital information in figuring out the structure of the molecule. This is determined by the splitting pattern. And lastly, you can, the chemical shift value. I mean, you can open the data booklet. I mean, this is the last thing that you should do. Analyze the chemical shift value, because that will also give you an information about what's the chemical environment. Whether there is the hydrogen protons are next to a serial bond or are they next to a double bond, whatever it is next to. Okay, so mainly it's these three, four things.
So yeah, what are these 3-4 things? Yeah, advantages of NMR?
Yes, sir. Sorry. Bhaskar, I'll come to splitting pattern. Ibraz, this is how the NMR spectrum is useful. Okay, what information do you get about the molecule based using the NMR spectrum? This is how you're going to solve the question. You're going to look at the chemical environments. Well, how did we end up solving this question? We looked at, well, he did give us some information about the alcohol, but we looked at that it had 4 environments. Then we looked at the splitting pattern, or the number of, we can also get the number of protons in those chemical environments. Then the number of protons on the neighboring, we can figure out the splitting pattern. And then we can also have a look at the data booklet and compare the chemical shift values. So all of this would be used to figure out what the structure of the molecule is. So Bhaskar, your point. Bhaskar, the n+1 rule was that if I have, sorry, hang on a second. Just hold on a second. I said the n+1 rule was that if I have hydrogen protons and the neighboring carbon has 1H, this peak over here will split into 2 peaks. Were you clear? Did you understand what we did yesterday?
See, yeah,
Yes.
points, 3 points of physics rank. Sorry.
नहीं वो यही सारे points है ना? Okay, what does this NMR spectrum tell you? It tells you that it's got 1, 2, 3, 4, 5 chemical environments. So that's 1, 2, 3, 4, 5, right? What does the splitting pattern tell you? That if it's a doublet peak, that means the neighboring carbon has 1H. If there's a triplet peak, that means the neighboring carbon has 2 H's. If there's a multiplet peak, that means that it's got a lot of neighboring carbon atom H's, right? If there's a singlet, that means either the neighboring carbon atom has no H or it's an OH or NH2 peak, because they're always singlets. You clear splitting pattern? Then